Welcome to Intro to Differentials. So the idea here is basically we want to approximate the change in y. So we want to approximate the change in y. So if we set, if we have a graph and we have our function, then we could pick 2 points on the graph. And then we have the change in x value, which I'm going to label as delta, Greek letter delta, which is just a triangle, x. And then we also have a change in y value, which is our change in y. So we could actually calculate the change in y. Right? So note, if this is the function f, the change in y would be we say this is at x equals a. Change in y would be f of a plus the change in x minus f of a. Right? It's just the y value of the second point minus the y value of the first point. Or we could approximate using the tangent line approximation. So if we did our tangent line approximation, we have our tangent line. And we could instead look at the y value there and approximate by using our tangent line approximation. So I'll draw a new picture with the tangent line. So our tangent line at x equals a is, we have y is equal to the derivative evaluated at a times x minus a, and then add on f of a at the end. Right, this is our tangent line approximation at x equals a. So I need to give myself a little more space. We can now figure out the approximation at a plus change in x. Right, so the second point we were looking at would be a plus the change in x, or delta x. So we have the approximation at x equals a plus the change in x, or plus delta x. We have the f of a plus delta x is approximately f prime of a times, we would plug in a plus change in x, and then subtract off a, and then add on f of a. So again, this a plus change in x is acting as my x. And if we simplify this, we get that the function value is approximately f prime of a times the change in x, and then plus f of a. So we could approximate the change in y right? So the change in y, again, was just f of a plus the change in x minus f of a. But we just figured out that f of a plus the change in x was approximately f prime of a times the change in x plus f of a. And then we have minus f of a at the end. So again, this f prime of a times change in x plus f of a is our approximation for f of a plus the change in x. That plus f of a minus f of a cancels out. So we wind up with the change in y is approximately just the derivative of f evaluated at a times the change in x. So I did mention that I would draw the picture for this. So off to the side. If here is a, and then a plus the change in x, we do our tangent line approximation. And so here's what we found as our approximation versus the actual value. So change in y is this big distance here. The total distance is our change in y. What we just found was this smaller distance right here. So this is our approximation. When we do this, sometimes we'll overestimate, sometimes we'll underestimate. That's going to depend on the concavity. But this is an estimate that we can find. So again, f prime of a times whatever our change in x is gives us a fairly reasonable approximation, particularly when our change of x is small for change in y. So now I'm going to go ahead and just define the differentials. So again, if we set change in x to be some number, usually small, and then we set change in y to be our f of a plus change in x minus f of a, right, the actual change in y. And then if we set dx simply to be that change in x, this is our differential for within x. Then what we can do is we can set dy to be what we just found, f prime of a times the change in x. And in fact, I'm going to swap out these a's now, and instead of using a's, we'll just use x's. So putting in an x instead in all of those locations, we'll do x plus the change in x minus f of x. And then f prime or dy will be f prime evaluated at x times the change in x. Okay. This again will be a differential in terms of y. And this is approximately, so this differential is an approximation for the change in y. And so what we'll wind up doing is we will use this approximation for the change in y instead of explicitly calculating that change in y. We have a variety of sort of situations where this is relevant. And then also these differentials will be extremely useful. These differentials will be extremely useful once we switch over to integration. So we'll have a few applications going forward, and we'll do some practice with finding differentials. In reality, it's not really any more complicated than finding the derivative, since dy is simply, I'm going to change, also note that dy is just f prime of x times dx, since we set dx to be the change in x. So all we're really doing is taking f prime of x, whatever f is, and then multiplying by that differential dx.